So now we're going to start section 1.4, and this is about arguments and what are called rules of inference. So I think the last few sections have felt very abstract, and maybe it wasn't entirely clear how this abstract idea of logic relates back to arguments and everyday kinds of logic. So that's what we're going to be talking about in this section. So how the formal logic relates to arguments that you might make. And we're going to be looking at this example, a silly little example, but it's a good outline for an argument. Because lots of arguments have this kind of structure that we're going to see. And here it is. If it's raining, then there must be a cloud above me. It's raining, therefore, there's a cloud above me. So it's a pretty uncontroversial kind of argument. Definitely, if it's raining, then we can agree there must be something dropping rain. But this kind of formal structure, this process, let's say, of drawing a conclusion, so drawing the conclusion that there's a cloud above me, has a name. The process of drawing a conclusion from a sequence of propositions is called deductive reasoning. So deducing something is the act of drawing a conclusion. And in deductive reasoning, we're worried about, or our primary concern is about whether our argument actually works. And formally, we have this word called valid for when that's the case. And an argument is called valid if the conclusion, so the last line of your argument basically, is guaranteed to be true by the hypotheses or the other parts of the argument. And sometimes we call these premises or premises. So in this argument here, the first two lines would correspond to the hypotheses. And something I want to point out is that in deductive reasoning, we use the word hypothesis in a little bit of a different way than you might be used to seeing it in things like the scientific method. So in the scientific method, a hypothesis is something like a guess. So you make observations, and then from those observations, you make a guess about how the world is. So like, if you're a physicist, you might observe the way atoms behave, and then you make some hypothesis, like maybe a mathematical equation that describes how they behave. But that's different from what I mean here. So in the scientific method, they're guesses. In deductive reasoning, hypotheses are more like the basis for the argument. So they're the reasons for your argument. what you're saying is, if your hypotheses are true, if your reasons are true, then your conclusion is true. So make sure that you make that distinction, that mental distinction between deductive reasoning and something like the scientific method. And mathematicians always like good notation. And we do have some formal notation to talk about for arguments. So you can see in this argument written out in sentences, I have more than one hypothesis and then a single conclusion. So when we're writing our notation, I'm going to need more than one hypothesis. And we'll give those the names P1 through Pn. Actually, I'd phrase this a little bit differently. Scratch this out. They are hypotheses, but I want to call them just propositions for now. So they're things that can be true or false, the kinds of things that we deal with in logic. And then maybe underneath, I'll label them hypotheses. And conclusion. And then our formal argument is set up the same way as I did in the example. So you list out your hypotheses. But when we're using symbols, we like to put a horizontal line to make a distinction between our hypotheses, and then our conclusion goes directly below here. So this is the symbolic structure. And I also need to explain what this little triangle of dots means. And this is the symbol in logic for the word therefore. So just like in my example, I wrote out the word therefore, and then I stated the conclusion. When you're using symbols, you'll use the 3-dot triangle instead. Any questions so far? I'll pause here in case some of you are still writing. Okay, so I guess I can assume we can move on. Okay, so in this first example, what I want to do is translate this argument into a symbolic argument. Actually, let's continue here. So what I want to do is replace the propositions in my argument with symbols. This first one, it's raining. I'm going to label P, excuse me. And then there must be a cloud above me. We're going to label this one Q. And then we can see that we've just repeated P on the next line. And the conclusion is Q. So let me go over to this page and write that out. So P is going to stand in for it's raining. Q is there's a cloud above me. And now I'm going to translate the argument from the first example into a symbolic argument. So let's take a look here. The first part of my argument is a conditional proposition. I'm saying if P, then Q. So going to the next page, the first line of my symbolic argument is going to be that proposition. But I'm going to write it out in symbols now instead of words. Then the second part of my argument, this line, is P. I'm saying it's raining. So I'm stating that it's raining is a true proposition. Okay. And then the last part is the conclusion. We get the word therefore. We'll replace that with 3 dots. And then we'll write Q for the conclusion. Any questions in how we translated?
Do you have to have the P and the therefore Q separated by the line?
Yeah, so the line is what we use to separate the hypotheses, so the first 2 lines, from the conclusion. That's what this represents.
Oh, okay. So it's kind of like a fraction, like you'd have the first part of the fraction and then the second part of the fraction.
Let's see. I think if I was looking for an analogy, I would think more like addition. So I'm trying to add these 2 propositions together to draw a conclusion. So you might think back to elementary school where you were adding numbers like this.
Okay, that makes.
Okay, so maybe you're wondering, why would I ever want to look at symbolic arguments when I could just read words that actually mean something? And there's actually a really good reason for it. It's because these kinds of structures, so arguments that have this shape, show up all the time in all sorts of arguments. And this next thing, rules of inference, these are basically a list of brief, valid arguments that show up everywhere. And you often use these short arguments, like this one, in order to build larger, more complex arguments. So the way that mathematicians look at things, and I'm assuming computer scientists are the same, we like to step back from a specific instance, so like a specific argument, and try to look at an overall structure instead and see how those structures relate to each other. Because sometimes when we can step back like this, we can solve lots of problems all at the same time. We only have to check the structure to see if it's valid a single time instead of looking at every single argument individually. Okay, so moving on to the example. So this argument structure, this is the same as what we had above us in the example. This gets a special name. It's called modus ponens. Please don't ask me to translate that Latin. You can Google it, but I don't remember what it is. But essentially, this is a really old kind of argument, so old that even the Romans gave it a name. So nothing that we're doing here is very new. We're just trying to learn it for ourselves. And what I want to do in the example is show that this is valid. And remember, valid has a very specific meaning in logic. It means that if the two hypotheses are true, then the conclusion has to be true. That's what we're trying to show. And in order to do that, we're going to go back to our idea that we've been using constantly of a truth table. Okay, so let me tell you what to put in your truth table, because we have not just a single proposition that we're making a table for, there's something like 3 propositions here. So what you want to do is look for your simple propositions, the component pieces, In this case, we have two of them, P and Q. And this is how you'll start your truth table, just like you did before. And then we're eventually going to add rows for each of the possible truth values. And what we need next are columns for the two hypotheses. And then another column for the conclusion. In this particular case, one of our hypotheses just repeats one of these, and the conclusion does as well. But in more complicated arguments, you'll definitely need to include all of the columns because you'll have something a little bit more complicated than just a single simple proposition. So it's a good practice to go ahead and include these, even if maybe we don't have to. So we fill in left to right just like normal, because this is the simplest part of the table, just the possible combinations of true and false. And then we'll fill in the truth values, starting with the conditional statement, if P then Q. And we know this to be true, false, true, true. The only false is where the hypothesis is true and the conclusion is false. And then we're going to fill in these two columns, and we'll just be copying on this particular example. Okay, so that completes the truth table. And now we need to look at it and answer this question that I'm about to write. We have to check that the conclusion is true whenever all of the hypotheses are true. So which rows correspond to all of the hypotheses being true?
The first one.
Right, just the first row. Let me go ahead and circle that one. So if both hypotheses are true, is the conclusion true?
Yes.
Yes, definitely. So now we're actually done. So we've checked that if both hypotheses are true, the conclusion has to be true. So since we do have this row where, I guess I don't need to repeat myself again. I've already said it a couple times. So we conclude that this is valid. Okay,
Professor,
yes, go ahead.
so I have the question. So the only thing is will be the valid when the hypothesis is true and the conclusion must be true also, right?
Right. So if both hypotheses are true, we have to double check that the conclusion is true. So if this wasn't valid, that means there would have been a false here in the conclusion column.
Okay.
Are there any other questions? Okay, so if there aren't any other questions, I think this is a good stopping point for us today. And we'll finish up this section. I guess it'll be a week from today, next Wednesday.